You know, we live in a world just jam-packed with electronics. But what you might not realize is there's this constant, invisible battle happening all around us between all our devices. So today we're going to pull back that curtain and take a look at this hidden world.
I mean, have you ever been like running the blender in the kitchen and suddenly the TV in the other room just starts going haywire? You know, with all that static and those weird lines dancing around? Well, that is not a random glitch. It's actually a classic textbook sign of electronic interference.
Oh, and here's another one I bet you've noticed. You put your phone down next to some speakers, and right before you get a text, you hear that weird bzz, bzz, bzz sound, right? That's your phone's signal literally getting picked up where it shouldn't be. And that little annoyance, it's a glimpse into a huge, huge challenge for engineers.
So yeah, that's what we're talking about, this invisible battle happening all around you. You can think of it like this. Every single one of your gadgets is kind of shouting. It's broadcasting energy out into the world. And at the same time, every other device is listening. The problems start when one device is shouting completely drowns out another device's quiet little conversation.
And that's where this whole field of electromagnetic compatibility, or EMC, comes into play. It's basically the art and science of making sure all our electronics can coexist peacefully, without messing each other up. It's about teaching our gadgets to play nice in a very, very crowded room.
Okay, so how does this interference stuff actually work? I mean, what's really going on? Well, what's fascinating is that every single interference problem, every single one, from your buzzing speakers all the way up to a critical aircraft system failing, it can all be broken down into just 3 basic parts.
Seriously, this simple 3-part model is like the secret decoder ring for solving any interference problem. Once you get this, you're going to start seeing it absolutely everywhere. All right, so here it is. You've got the source. That's the thing making the unwanted noise. Then you have the receptor, which is the device that's getting messed up by that noise. And connecting them is the coupling path. That's the route the energy takes. And here's the magic trick. To fix the problem, you just have to break one link in that chain. That's it. Either shut up the source, protect the receptor, or block the path. Okay, let's use an analogy to make this crystal clear. Think about being in a quiet library, right? You're trying to read, totally focused, and then someone starts talking really loudly on their phone nearby. So annoying, right? Well, guess what? That is exactly what's happening with our electronics all the time.
This maps perfectly to our model. The loud person on the phone? That's your source. The air carrying the sound of their voice? That's the path. And you, the person trying to read who's now totally distracted? You're the receptor. See, the interference isn't just the sound, it's the fact that the sound is causing you to do something you don't want to do, which is lose your concentration.
So, if we want to build these good electronic citizens, how do we do it? Well, it turns out it all boils down to what I like to call the 3 golden rules of EMC. These are the absolute bedrock design goals for any electronic device.
All right, for a device to be truly compatible, it has to nail all 3 of these. Rule number 1, it can't cause interference with other stuff. Simple, right? Don't be the loud talker in the library, be a good neighbor. Rule number 2, it can't be easily affected by interference from other systems. It needs to be tough enough to do its job, even when the world around it is noisy. And then there's rule number 3. And this one's a little sneaky, but so important. It can't cause interference with itself. Think about it. A modern smartphone is like a packed city of tiny components. If the powerful processor starts shouting at the delicate little radio receiver right next to it, the whole phone can just fail from the inside. So a device has to be at peace with the outside world and also at peace with itself.
Okay, let's dive a little deeper now. We can actually break down all this noise into 4 main types of problems. And understanding these 4 categories is how engineers figure out exactly what's going on when things go wrong.
So when you look at these 4 types, they really come from answering 2 simple questions. First question, is your device the bad guy causing the problem, or is it the victim? And the second question is, how is that pesky interference actually getting from point A to point B? So let's tackle that first question. We call it emissions versus susceptibility. Emissions is when your device is the problem. It's the source. It's putting out way too much electronic noise. That's why governments have all these rules about how much noise a new gadget is allowed to make. On the flip side, you have susceptibility. That's when your device has the problem. It's the receptor. It's just too sensitive to all the noise that's floating around out there from other devices.
And now for the second question, the path. We split this into radiated and conducted. Radiated interference is when the noise travels through the air, just like a radio signal. Conducted interference is when it travels through physical things like power cords and cables. Now, let's have a little aha moment and go back to our first examples. Remember the blender messing with the TV? The blender's motor is creating noise that's both radiated through the air and conducted through the house's wiring. And the phone buzzing in the speakers? That's a perfect example of radiated susceptibility. The speakers are just too susceptible to the radiated energy from your phone.
Okay, so far this might all sound a little bit academic, right? But now let's talk about the real world. Because when engineers get this stuff wrong, the consequences can be, well, they can go from just plain annoying to downright catastrophic.
I'm serious. We're talking about times when this invisible battle spills over into our physical world, and the results can be incredibly serious, even life-threatening. Let me give you a couple of really mind-blowing examples from the history books.
Get this. There was a case where a truck driver using his CB radio would sometimes cause the brakes on his own truck to lock up. I mean, just let that sink in. A simple radio signal was powerful enough to seize the brakes of a huge truck. That is a terrifying real-world example of radiated susceptibility, where the electronic braking system was just overwhelmed by a radio signal it was never designed to handle.
And here's another wild one. A big computer system was set up near an airport, and it kept losing data or storing the wrong information. Nobody could figure out why. The problem was happening in perfect time with the sweep of the airport surveillance radar. That powerful radar beam was literally hitting the building, getting into the poorly shielded computers and corrupting the data. They had to spend a ton of money to add a whole bunch of shielding to fix it. So you see, this is the really critical takeaway. EMC isn't just some boring government regulation you have to check off a list. That's just the starting line. Real, good EMC design is all about building products that are safe and reliable. It's about making tech that we can actually trust to work the way it's supposed to, no matter how noisy our electronic world gets.
And that really leaves us with a huge question to think about, doesn't it? Because as we pack more and more technology into our lives, into our homes, our cars, even into our own bodies with medical devices, this invisible battle is only going to get more intense. So the real challenge moving forward is, in a world with billions of devices all screaming at each other, how do we possibly design for electromagnetic peace?